task 1, 2, 3. Those are given to you. What you have to do is writing some assembly code for context switching, initialization and context switching. Okay, so for task scheduling, you are supposed to use an timer interrupt, right? Private timer. Okay, this one, periodic, timer interrupt. So you know everything you need to know by this time to do this class project. Okay, but this one is not mandatory. This is optional. But if you finish it, reward is huge, right? 10% with final credit, huge. So if your midterm performance is not good, exam performance is not good, I think this is a good opportunity to make up. Okay. So try to do this, but don't wait until the last minute because it takes time. It really takes time. So don't wait until the last minute. And really, 10%, right? That is huge. 10% extra credit, extra. Okay, let's get started. This one. We are talking about interrupt, right? So interrupt. There are two kinds of interrupt. First one, hardware interrupt. Second, software interrupt. Software interrupt. And software interrupt is provided as an instruction. In ARM case, we have SBC instruction, supervisor call instruction. And hardware interrupt is typically generated from IO devices. Okay. So last time we went through the one example, right? Interrupt from private timer. And today we will talk about another flavor of hardware interrupt that is called, in ARM terminology, SGI. This one stands for software generated interrupt. This one stands for software generated interrupt. So it sounds like software interrupt, right? Software generated interrupt. So it seems like these two are the same, right? But it is not actually. So this one is hardware interrupt. Because that interrupt is delivered through that IRQ or FIQ interface. The SGI, software generated interrupt. It is very simple. Okay, so let's go through this PowerPoint slide from this PowerPoint slide. This one. Okay, Konuk. Okay, thanks. In GIC, generic interrupt controller, right? So ARM is providing GIC, and in GIC, there to be 1,000. Remember, 1,020 interrupt sources, right? And unique ID is assigned to each IO device. And for example, right, number 29 is is assigned for private timer. Private timer. So unique ID is assigned to each IO device. So according to ARM specification, number 0 to ID number 50, that is assigned for software generated interrupt. So that is a rule, right? So 0 to 15. And from ID number 16 to ID number 31, these 16 are assigned for IO devices, but private IO devices. Private, meaning that CPU, some IO devices are private to that specific CPU. There is a private timer for the CPU, and there is a separate private timer for CPU number 7. It's private, separate private timers, right, for each private timer for each CPU. And from ID number 32 to ID number 10, 19, these are also assigned to IO devices, but shared IO devices. Sure. Right? So from ID 16 to 10, 19, okay? These are IO devices, the interrupt sources from IO devices. And that is assigned, that is reserved for software generated interrupt. So we are talking about this software generated interrupt. How to generate SGI? It is super simple. So this one, Minseong? Minseong? Yes. Yes.
Using SGI, the other for CPUs using a software generated. There are 60 software generated interrupts, equals 7-1. And SGI is generated by writing the SGI interrupt number to the ICDSDIR register and specifying the target CPU. This write occurs via the CPU's own private bus. Each CPU has its own set of SGI registers to make one or more of the 16-bit software generated interrupts. The interrupts are cleared by reading the ICIR interrupt technology register or writing a 1 to the corresponding bits of the ICDICTR interrupt cleared into register.
Okay, thanks. It sounds very complex, but it is not. So let's talk about what is SGI. So application first. Let's read this one first. So let's read this PowerPoint and let me explain. This one, Harima. Okay, and next one. This one. Inchang. Yes. There is application, the SGI application examples. This one is, I think, very important. Juna? Yes, please. Okay. So how to generate software generated interrupt. It is very simple. There is a register called in distributor. There is a register called SGI, software generated interrupt register. So you write some value to SGIR and interrupt will be generated. It is that simple. So there is a format. So take a look at this. You can specify the ID. So these 16 IDs are reserved for SGI. So what number, what ID do you want to what number do you want to generate interrupt with? Right? ID number 0 or ID number 15. Okay. ID number 3, 4, anything. So here you program ID and you specify. So this green and purple. Okay, you specify the target CPU. So who do you want to send that interrupt to? So for example, if you set 00 to green, then you have to look at this CPU target list. Okay? So there is 8-bit target. Okay? Because GIC was architected with 8 CPUs in mind. And you have 8 CPUs. Okay? So for example, if you program 7 zeros and 1, then you want to send that interrupt to CPU number 1. So CPU number 0. Okay. So each bit is corresponding to each bit is corresponding to one CPU. This one CPU number 0, second bit CPU number 1, the last one CPU number 7. So if you set last bit to 1 and first bit to 1, then you want to send that interrupt to CPU number 0 and CPU number 7. That's it. And then first 2 bit is green. Right? So green, if you set green to 00, then you have to program the target in this purple, orange, okay, and 01. Then that interrupt will be sent to everyone but yourself, okay, except yourself. Okay. If you set this bit to 10, then that interrupt will be sent to yourself. Okay, to yourself. For example, CPU is writing this register with 10 here, 10, and that interrupt will be sent to itself. So by programming this register, interrupt is generated. So that is why it is called software generated interrupt. You're writing some value, okay? Then interrupt will be generated. Then why do you want? Question is, why do you want to use that? Why do you want to generate that kind of interrupt? Okay, this one. So that interrupt is used to. So SGI is used to generate IPI. So inter-processor interrupt. Assuming that you have 4 CPUs in a system, there's an interrupt controller. By writing some value to SGIR, you want to set the interrupt from CPU 0 to CPU 1, or CPU 0 to CPU 2, or CPU 3. Okay? Or itself, right? CPU 0 writes a value and send interrupt to itself. And what is the application? So application, these 4 are application cases. First one is startup IPI, inter-processor interrupt. Think about your smartphone or notebook computer system. There are 4 CPUs or 8 CPUs. When you boot up your computer system, only one CPU is alive, typically. And that one CPU is doing initialization. After that, it is waking up other CPUs. To wake up other CPUs, that CPU, let's say CPU 0 is alive at the beginning. That CPU is sending interrupt to CPU 1, CPU 2, CPU 3. That is inter-processor interrupt, IPI. And second example is task dispatch. You think about operating system and task scheduler. There are two tasks. Some tasks. There is some task you want to run on CPU 1. Then probably operating system send interrupt to CPU 1 and task scheduler in operating system, right? Task scheduler will be invoked and task scheduler will assign the task to CPU 1. So that is typically used, the IPI is typically used in operating system for task dispatch. Assigning some task to CPU 1, to CPU 2, or to CPU 3. Okay. And third one is a little bit tricky to explain. TLB shutdown. How many of you know TLB? Translation look aside. How many of you took architecture class from me last semester? Some of you. Okay. So we didn't have time to talk about the virtual memory support. Okay? So in CPU, we will talk about TLB in this class. In processor, we have, let's say, multi-processor system, two processor system. Okay? Processor number 0 and processor number 1. And you have a CPU core, then cache. Also, you have super important hardware called TLB, translation group assign. TLB, translation group assign. Okay. That TLB is used to do what? You have a memory, and in memory you have a page table loading somewhere. There's page table. Okay. TLB is caching. TLB is loading the frequently used entries in page table to here and to here. So TLB is a cache. TLB is a cache for page table. Okay. And TLB is a super important component to support virtual memory. We will talk about that later on. But the thing is, what is that? TLB shutdown. What if this processor changes? That guy is caching. Let's say it is caching first entry and second entry. Okay, 1 and 2 here. And that guy also caching this entry. First entry, first one and second one in page table. What if the page table is modified by processor? Okay. So that entry got modified by CPU processor to that cache. So because that guy modified it, so here this guy TLB knows, right? 2 prime. But how about this guy? This guy doesn't know the modification of the second entry. Okay? So to make these entries coherent, you need to send IPI to the other processor and ask that processor, okay, you need to flush out. That entry is not valid anymore. You have to flush out. That is called TLB shutdown. We will talk about TLB later on. Okay. So after cache discussion, we will talk about page table and some programming. Okay. So IPIs are very frequently used in computer system. Okay, IPIs. So any question about this application? Okay, let's move on. Then once you generate IPI, once you generate SGI, then the interrupt processing follows standard procedure. Right? You have acknowledge register, interrupt acknowledge register, and end of interrupt register. So in ISR, right? So interrupt is generated. SGI is generated while executing some program. Right? Then you jump to ISR. In ISR, what you have to do is you read interrupt acknowledge register to figure out the interrupt ID, right? Who generated the interrupt. Then that acknowledge register contains not only this ID, not only that ID, not only this ID, that ID, not only that ID, but also CPU ID. Who requested that interrupt? Right? So CPU 0 can send the interrupt to CPU 7, right? Or CPU 7 can generate IPI to CPU 0. Then CPU 0 read interrupt acknowledge register. And by looking at this CPU ID, that CPU 0 figure out, okay, you, CPU 7, you sent me an interrupt. Okay, assume that your CPU 7 generates the interrupt by writing SGI like this. That is IPI. Right? Then CPU 0 need to figure out who sent me interrupt. Right? Okay, you are the one. Okay, who generated interrupt? Sent me interrupt. So by reading acknowledge register, you figure out two things, right? Interrupt ID. Right? So one of these, right? One of these actually, right? Interrupt ID and who sent interrupt, which CPU sent interrupt. In case of SGI, who sent interrupt to me? And at the end of interrupt processing, you have to update, right? EOIR, right? You have to update end of interrupt register. That means you are notifying CPU interface. Okay, I'm done processing that interrupt. Okay, so let me show you a demo, simple demo. This demo would be very simple. This one, SGI project, SGI. Okay, so this is the one I created, this project. We use our own interrupt vector table. And before setting up a vector base register, I'm disabling, right? Change processor state and interrupt disable. So I bit, right? CPSR I bit will be clear to 0. Sorry, set to 1. Okay, set to 1. Set to 1 to disable interrupt because I'm doing some initialization, right? Until I'm doing initialization, please don't. I'm not going to take interrupt. That is a message, right? So after that, I'm setting V bar register and changing operating mode to IRQ, set up stack pointer, change system mode, and then GIC setup. Right? So I'm reading something, LDR, then distributor global enable. Right? That distributor, I want to make it active first. That distributor global enable. Distributor enable. Then if you scroll it down, I'm sending this interrupt. This is the code generating SGI. Right? So that is the one. Store instruction to R0. Software generate interrupt register. Then what data? R1. R1 is written to R0. Okay, that register. So compare that code with this PowerPoint slide, right? So I'm trying to program what? The green part will be 0, 0. 0, 0 means you need to look at target, right? Target list, this one. So that starts from bit 16. bit 16 to 8 bit, right? So I'm doing this. 1, then 16 bit shift to the left. Okay, to position 1 to that location, 16th, right? That location. Okay, so I want to do what? I want to write this value. 7 zeros and 1. Target. That means target is this guy, CPU 0. This guy is writing, updating SGIR, and interrupt will be sent to itself. Okay. Originator. Then interrupt ID, right? This purple will be 3. ID number 3. This one. Okay, interrupt ID. So that means I need to program corresponding registers. Okay, corresponding register. ID number 3 related, right? ID number 3 related registers in distributor first. So remember, in private timer case, you need to touch number 29 related register, right? Priority register, and enable register. Remember, enable register. So we are talking about ID number 3. That means you need to touch number 3, ID number 3 related registers. Priority. What is the priority of that ID number 3? So scroll up. Then, so that is again a global enable. I want to make distributor active, right? That is enabled. Then priority register. So we are talking about ID number 3, right? So each register is holding 4 bytes, right? So that is priority number 0 register, 4 byte register. The first one is for ID number 0, 8 bit, right? 1 byte. And this one, ID number 1, 2, 3. So we are talking about ID number 3. So you need to touch that byte. Okay. So that is why I'm doing 24-bit shift left. 24-bit shift left to update, that specific byte with 8. So priority of ID number 3 will be 8 in that example code. 8. Okay. Then that is about distributor setting. Then CPU interface, right? CPU interface global enable to make it active. It's hardware module. You need to make it active, right? So distributor is forwarding interrupt, then there is active, then you can do, this guy will do some comparison. You have what? Priority mask register. PMR. You are setting some threshold. So in that example code, I think I get FF, right? FF is a threshold. So the incoming, the interrupt priority, incoming interrupt priority will be compared against the guy. If the priority is higher than this guy, that interrupt will be forwarded to the CPU. Right. So priority mask register is set to FF. FF is the lowest priority. The lower the number is, higher the priority is, right? Lower number, higher priority. So FF means whatever you send me, whatever you forward, then I'm going to, FF means whatever you forward to me, then I'm going to forward that interrupt to CPU 0. Because FF is the lowest priority. Then finally, I'm generating SGI, right? Software generated interrupt. Then what is this? The interrupt enable, right? GPSR IB to 1, change operating mode to user mode, then forever loop. And while CPU is executing this forever loop, so in the previous code, you wrote, you updated SGIR. Then it will take some time to forward for hardware to forward that guy into CPU interface and CPU interface to CPU 0. So you have to wait, right? You have to wait CPU 0. So let me download it to the board. Okay, stops here. Then let me set breakpoint to, I already set breakpoint here, right? Let me check. Line number 20. Okay. And press F5. Okay. GIC setup. Then CPU interface setup. Right? Then I'm generating SGI, right? Software generated interrupt. Then if I press F5, some data, the data will be written to SGIR register. Then hardware is doing some preparation. Okay, trying to forward that interrupt to CPU interface, right? And then CPU interface is doing some comparison. Okay. Private is comparing with private master register to make decision forward or not. Right? So it will take some time. Right? So while hardware is doing that, CPU is doing this, running this idle loop, right? So let me press F5. Then let me press F8. Then eventually interrupt will be generated. Then it will stop at that breakpoint, right? F8 stops almost immediately, right? Then it is jumping to what? Interrupt service routine. Okay. So push CPU context to the stack, store multiple, right? And check out this register. Okay. So acknowledge register. So if I press F5, then what do you expect? R3 contains what? R3. So according to, so we programmed what? We programmed number 3, okay, ID number 3 to this register. So we are expecting 3, I think. Right? You are reading this acknowledge register, acknowledge, and CPU 0 sent that interrupt. So ID is ID. So ID 3-bit ID, right? 0 to 7. One of these 0, one of these number, right? 0 to 7. Because CPU 0 set that interrupt. So CPU ID contains 0. Then ID field, interrupt ID, one of these numbers, 0 to 1090. We are talking about ID number 3. 3 will be rotated in R3 register. Right. So press F5. So R3, right? R3, 3. Okay. Then LED toggle, right? So we are doing simple operation. LED. Okay, turned on, right? LED is turned on. 2 LEDs, I think here. 2 LEDs on. Then end of interrupt, register update with the same value, R3, right? Same R3. R3 hasn't modified R1, R2, so R3 still same R3. So we are updating end of interrupt register with the same number. Okay. Then pop from memory, right? To restore the CPU context. Then return back. You are keep executing this, right? Okay. Okay, that is a demo. Any question about SGI? Very simple, mechanism, right? You are updating, you are writing some value, then interrupt will be generated. That will be sent to any CPU, depending on the number, data you write. Then let's go through this PowerPoint slide. I need to talk some more about distributor and interface. So we already know about this. Let's talk about priority. This one is a little bit important. Priority. This one. 낙원. 동욱, 김동욱, 경화. Okay, please. Okay. I already explained to you, right? In GIC, generic interrupt controller, you have 8 bits to specify priority for each interrupt source, right? For each interrupt source. But depending on the product, the actual product. Remember, Arm is doing IP business, intellectual property business. So Samsung is purchasing that license, then Samsung can customize it. So depending on the final product, that can be a little bit, adjusted. So 8-bit is provided, but in case of Cortex-A9, the CPU, the processor we are using, it is implementing 5-bit version priority. So 32 different priorities, not 256. With 8-bit, you can specify how many different priorities? 0 to 255. But in because 8, right? 2 to the power of 8. 256 different priorities. But in Cortex-A9, Cortex-A9 is providing 32 different priority levels. So you can specify that. So in bit 7 to 3, you can specify priority. 7 to 3. That means last 3 bits will be ignored. Right? You specify, you use only 5. It's 5 bits to specify priority. Last 3 bits will be ignored. So 32 different priority levels. Okay, then let's talk about. So we already know about this priority register. Right? Each register is 32-bit or 4 byte in size, where you can specify 4 different priorities, right? So 4 different priorities for 4 IO devices. And you have a priority mask register. Priority mask register. Sorry, here in distributor, you set priority of each IO device. Okay, and in CPU interface, you set threshold with PMI. Okay, and then one more. So this one. 인사? 황인사? 오병진? 노정은? 오케이.
Group priorities and sub priorities. So group priorities
Okay, thanks. Using BPR, binary point register, you can split. You can where's that? You can split priority into two parts. Two parts. The first one is group priority, and the second one is sub priority. Group and sub priority. For example, if you specify here the BPR register, if you say you set set 1 to binary point register, that means upper 6 bit will be used as a group priority, and last 2 bit last 2 bit will be used as a sub priority. So using BPR register, you split priority into two parts. Group priority and sub priority, and that is used to do preemption. I think you have heard about this preemption in operating system course. Let's read this and let me explain. Madi. 호준? 이호준? Where are you? Where are you? Oh, you are. Okay. Okay. Okay, what do you mean by preemption? How many of you heard about preemption? Right? That is taught in operating system course, right? So let me explain with this example. Let's assume two tasks are there are two tasks, task A and task B. And task A has a low priority, and this one has a high priority. And let's assume that CPU is in the middle of executing task A. Okay? CPU is in the middle of executing task A. And then at some point, task B kicks in. Higher priority task kicks in. And what do you have to do? Operating system will stop at task A, then execute task B. In other words, task A will be switched out from CPU, and task B will be switched in. Switched out, switched in. So in other words, we say task A got preempted because higher priority task, that came in. I need to run higher priority task first. That is obvious, right? So preemption. Same thing is supported in GIC. Let's assume that there are two IO devices, timer and UART. And let's say UART has low priority and timer has high priority. Then timeline. This is time. And UART interrupt is generated at this point. UART. Okay. Then that interrupt will be forwarded to CPU interface, and CPU interface will forward that into CPU 0. If the threshold, if priority is higher than this threshold. Okay. Then CPU will execute some interrupt service routine or UART, right? CPU is in the middle of executing UART handler. And then while CPU is executing UART handler, assume that timer interrupt is generated. The timer interrupt, higher priority interrupt than this UART. Then what do you have to do? What do you think? GIC recognize that interrupt, then figure that, okay, timer has a higher priority. So that interrupt will be forwarded to CPU interface. But the problem is, CPU is in the middle of handling that's UART interrupt. So that means end of interrupt has not been updated yet. Right? So after ISR, after UART handler, so almost at the end of UART handler, you are supposed to update end of interrupt, informing that, okay, I'm done processing UART interrupt. But before that, assume that before that, timer interrupt is generated. Then what do you have to do? CPU interface is supporting preemption. If the interrupt is higher than currently running interrupt, that will be forwarded to CPU. If the interrupt is higher than currently running interrupt, okay, then that will be supported. But there are conditions. Two conditions should be satisfied to forward that interrupt to support your preemption of forward that interrupt to CPU. So two conditions are this. Preemption pending interrupt will be signaled only if the both conditions are satisfied. If priority is higher than this priority, timer interrupt priority is higher than this PMR threshold. That is obvious, right? And second condition is group priority using BPR register. Using BPR binary point register. You split priority into two parts, right? First one, group priority and sub priority. So we are talking about that group priority. If the group priority is higher than that of running priority. So in this example, if timer's group priority is higher than UART's group priority, then that interrupt will be reported. So it is supporting some preemption. GIC is providing preemption. Okay. So any question about this? Then what happens will be like this. So you are executing some program, then UART interrupt generated. So eventually you are jumping to UART handler. So in the middle, timer interrupt is generated. That interrupt will be notified to CPU if these two conditions are met. Only if these two conditions are met, right? Then what will happen? We are assuming CPSR I bit is clear to 0. Then your handler is allowing nested interrupt, right? So then it is jumping to, eventually it will jumping to timer handler. Okay? So execution flow looks like this, right? So timer handler will be executed first. Then after that, you are resuming your handler. Then you are resuming that interrupted place. So nested interrupt processing, right, with preemption. So this one is higher priority and lower priority. So from CPU point of view, right, CPU point of view, through this connection, this GIC should inform that interrupt occurs. So interrupt occurrence should be notified to like this, right? To CPU. Otherwise, CPU does not recognize that interrupt occurrence, right? Then that interrupt notification will be that notification will be announced if these two conditions are satisfied. Any question about this preemption? Okay, one last slide. So this one is about programming guide. The thing is, if you look at the data sheet, right? GIC data sheet, there are so many registers implemented, right? Check out this, technical reference manual. By reading that data sheet, it is very hard to figure out what register you touch and in which order, right? So sometimes data sheet is providing some programming guide. You have to touch that register first, and second this register, and this one next, and so on. Because there are so many registers, and you haven't designed interrupt controller. Someone else, architect, designed this GIC. Right? So we want to use that, but by looking at the specification, very hard to figure out. It's so complicated. It looks complicated. So there is a programming guide, right? This one is programming guide. So first one, global setting. So what it says is, okay, so enable this distributor first, then touch those registers, CPU interface, and enable this, okay, this one CPU interface, and program priority mask register, and also binary point register, PPR, if you allow preemption, interrupt preemption. And finally, there is a enabled it, right? Inside the CPU, you have a CPSR, IP, right? You have to clear that with 0. So there are many enablers, right? Inside the CPU, IB enable, right? CPU interface, that module enable, and distributor, that module enable, global enable, and also individual interrupt source enable. There are many different enablers, right? You have to make sure everything is enabled correctly. And then, this one, then programming guide, individual interrupt configuration. Using set enable register, you need to make sure, for example, this ID number 29 is enabled if you want to use private time. And you have to set corresponding priority register. Number 29 related, directly related, priority register. And sometimes target register. If interrupt source are shared. So number 31, this one. That is IO interrupt, but shared IO. And 16.2, number 31. There is also IO interrupt, but there is private IO. So in case of private IO, you don't have to specify the target, because hardware already know private, right? Some IO devices are private to the CPU. Same, private timer are present for CPU 0. Same private timer for CPU 7. Same one for CPU 6, 5, and so on. So each CPU has its own private timer. So you don't have to specify target in this case, in case of private IO. But shared IO means, these IOs are shared by these 8 CPUs. So in that case, interrupt is generated, then you have to specify the target. Okay, number 31. Who do you want to process that interrupt? CPU 0 or CPU 7? Which one? Who do you want to process that interrupt? You have to specify the target. And this edge trigger, level sensitive, it is a little bit tricky. Very hardware related register. Edge sensitive means interrupt line goes up, then interrupt controller recognize that as interrupt occurrence. The line goes high at this point. That is edge sensitive or edge trigger. And level trigger means as long as the line, interrupt line is high, asserted, then GIC, think of it as interrupt occurrence. It's a level sensitive interrupt. It's level. Time, for example, private timer is connected. Then countdown happens, then line goes up. If configuration register says edge sensitive, then at this point in time, interrupt is recognized. Okay? But set that be to level sensitive, then this line, as long as this line is high, then that is recognized as interrupt occurrence. So you have to make sure that status register, right? Clear the status register to pull down. Okay. Then when you take interrupt, the standard procedure, right? So read acknowledge register in ISR. And at the end, you need to touch end of interrupt register. So before that, you need to touch the interrupt source. Right? Interrupt source. But for example, private timer generated interrupt, you have to clear that bit, status register, stick it, pull it down, pull this interrupt line down. And if you want to allow nested interrupt, then you have to make sure. Right? CPSR IV2. Okay, nested. So some rules, right? So there is one I already explained to you. The last thing. So I told you, right? There are two interrupt inputs in ARM. Right? So here you have IRQ, right? IRQ and FIQ. Then so far we send interrupt through this IRQ line, but by writing some register, you can deliver interrupt to CPU through that FIQ line. Okay. Which register you have to touch? Simple. This one. This one, check, please. Okay, you can assign each interrupt to group 0 or group 1. Okay, by using this register, group register. For example, interrupt 31. Okay, I'm going to assign that as group 0 interrupt. So group 0 interrupt. This one group 1 interrupt. By touching that group register, you can assign each interrupt source to group. And group can be folded, right? Look at this. Group 1 interrupt is always delivered through higher drive. And group 0 interrupt can be delivered either through this or that line, depending on the setting. FIQ, EN setting, that is setting. So it is, everything, almost everything is programmable. Okay. So far we used only this IRQ or interrupt delivered through IRQ. By default, everything is delivered through that IRQ. Okay, that is about interrupt vector. You can skip this, I think. Okay, anything? Yes. So SGI register question is the ID, right? You need to program some ID. Then target also, right? So target, right? You have to specify target, not only this ID, also target. So in our JDBoard system, we have two CPUs, CPU 0 and CPU 1, and only one is enabled, CPU 0, the booting time. So in our demo code, I program target is 7 zeros and 1, meaning that I want to send that interrupt to myself. So you have to specify two things, right? ID. Yes. Yes. What do you mean by that? Writing some value 2 times here? So, okay, so what you're saying is, show you. 정훈? No? 해창. Okay. So what you're saying is this one? Writing this one twice? Like this? So what do you mean by that? Same content? By store instruction, right? 2 times. I don't know. You have to do some experimentation. So my expectation is only one interrupt generation. I don't know, but because I haven't designed that hardware, so don't know for sure. But you are updating this register. You're updating this register. So if we have clock, right? Clock is running like this. So GIC also has a clock, and updating probably here and updating probably here. Too short, right? Then first update, right? First store instruction, the second store instruction. So update, right? And when you update this register, then hardware will do something. Prepare, right? Prepare to forward that interrupt to CPU interface. Then it takes some time to do some comparison, right? So before that, you are updating this guy, right? What do you mean by that? Yeah, another interrupt will be generated. After processing this ISR, right? So at this point, right? So at this point, you are generating SGI, right? SGI, then it will eventually jump to interrupt service routine, then return back to this forever loop. Then probably here, right? You want to do the same thing, right? Copy this and paste here. Like this. Right? But this forever loop, right? You keep updating SGI register. Then this interval is too short, I think. Interval, right? So what is the point? You keep generating interrupt. Then you're not allowing enough time to process ISR. Right? So it is an issue like this, right? CPU is running let's say CPU is running at 1 gigahertz. 1 gigahertz. Then interrupt, right? IRQ, FIQ. So let's say that is 1 gigahertz. 1 gigahertz means clock period 1 nanosecond. So what if interrupt is generated too frequent, right? So here interrupt generated, then IRQ. What if another interrupt generated like this? So interrupt is generated, then CPU try to jump to ISR. Then before you process ISR, you are generating another interrupt. This interval is too short. Then system design is actually wrong. This is not, correct system design. It's supposed to be CPU is supposed to be super fast in your system, the fastest component. Right? Interrupt. Think about I/O interrupt. I/O interrupt, keyboard interrupt, mouse interrupt, right? Network. The interrupt from network card. Packet comes in. Right? It takes some time. It is not supposed to be faster than CPU, or the interval is not supposed to be that short. Is it you are asking what? At the end, okay, at the end of interrupt service routine, right? Let me remove this. So at the end of interrupt service routine, at this point, here, update SGIR.
I know.
In SGI case, right? SGI case, what you're supposed to do is update only EOIR, read IAR, to figure out who generated the ID, interrupt ID. Then at the end, you are updating EOIR. Right? That is the protocol you have to follow. So in case of SGIR, right? SGIR is not coming from IO device, right? There is no sticky bit. Okay, you don't have to clear that specific IO device because it is coming from your program, right? Your program is updating this register. Then IPI is generated. And then the data sheet is talking about in case of SGI, what you have to do is read IAR to check out ID. Then at the end, you will have to update EOIR. Is it still strange? Okay. Okay, any other questions? Yes. GIC. Excellent question. What do you think? Excellent question. What do you think? Okay. So in case of SGI, okay, the question is, what if in multiprocessor system, right? CPU 02, CPU 7, 8 CPU. What if these 8 guys are trying to update same register? And what do they do? Very strange, right? So CPU 0 is trying to update ID number 3. And that guy is trying to update ID number 5. Target will be changed as well. CPU 7 almost at the same time because separate physical CPUs. 8 CPUs are trying to update that guy at the same time. What do they do? Very strange, right? That's why the thing is there are multiple copies of that same register for each CPU. So you have actually 8 SGIR at the same location. We call that banked register. So the offset, I don't know offset, maybe 100 and putting up. The same, this one is for CPU 0. Okay. Same register for SGIR for CPU number 1. Same offset 100. So CPU 1 is updating the register. CPU 0 is updating that register. CPU 7 is updating the rest. So each CPU is touching different register, not same register. So check out this manual. Search with banked. So banked interrupt or banked register. So register banking. Banking refers to implementing multiple copies of the same register at the same address. Search with banked. Look at this. ID number 0 to ID number 31. That is SGI, right? Interrupt number are used for interrupt CPU interface. These interrupts are banked in distributor. That means there are multiple copies. Because you have 8 CPUs, you have 8 equal copies at the same location, 100 offset, 100 offset. So CPU 0 is updating this guy, CPU 1 is updating only this guy, not this guy, this guy. CPU 2 updating this one, CPU 7 left. Excellent question. Yes. There are some banked registers in GRC. I haven't talked about that banked register, but there are some banked registers. Any other questions? Yes. So you have to make sure. You have to make sure. So it is related to very good question actually. So let me explain with cache coherence issue, not TLB coherence because it'll be complicated. But same issue, cache coherence and TLB coherence, right? Same issue. Right? So what you have to do is CPU, right? Number 0, CPU. Number 1, cache. Right? Cache is temporary storage. Right? So load memory block. Right? So cache. So it is reading. Assume that you are doing LDR. Right? Load from some memory location. And let's say this memory block that will be loaded into the cache first. Okay? This one. And then load it into some register. So loading from this location and place into alt register, same thing. Right? So you are reading LDR from the same same location, right? So same copy will be loaded in the cache first, and will be loaded in the CPU. What if this guy is doing store operation, update, writing some value? Not this guy, maybe 2. Let's say number 1 and number 2. So that guy is then contains the stale information, not updated information. So for that, what do you have to do? Hardware is providing cache coherence protocol. So before you update, you have to make sure you are invalidated. It is not updated yet. You have to make sure, okay, it is stale copy. You have to invalidate. It is sending some invalidation request to the CPU. Then cache that line, cache entry will be invalidated. Okay. Then after that, you can update this guy. After invalidation, you can update, cache will update 1 to 2. Then next time, CPU 1 read the value, then that data is not in the cache. So you have to read from memory, but memory does not contain the up-to-date information, not latest information. So that guy is requesting some data, and that request is seen by not only this memory but this guy. So cache will provide the data. So that is cache coherent protocol. The similar mechanism will be applied to TLB. Right? So before updating page table, you have to make sure you invalidate the guy first. Yes, invalidation is done, right? How to invalidate? Cache coherence is provided by hardware, but TLB invalidation is not provided by hardware. It should be done by software. That is why you are sending IPI. IPI, then CPU get interrupted, then interrupt service routine. You have to flush out TLB. Okay, a little bit advanced. I don't know if you are following me or not, but that is what's happening. Okay, any other question? So this is about that concludes interrupt discussion from Thursday's class. We will jump into the topic. Cache first, and then here or virtual. And after that, security feature for the trust zone. Okay, that is it for today.
좀 이상하고 있어서. 볼트 모드가 어떨 때 들어가요?
어볼트 모드는 어볼트 때.
제가 그 이제 URT로 보내는 코드를 C로 짜서 그 ISR에서 브랜치 링크 인스트럭션으로 잡다가 와서 뒤에 인스트럭션을 다 똑같이 했거든요. 교수님 그 똑같이 R3도 그 DL 하기 전에 그 R1, R0부터 R12까지 다 스택에다 백업해놓고 나와서 다시 복원하고. 근데 이제 PC 서비스 PC를 그거를 하니까 오버트 모드로 들어가게 되더라고요. 그래서 제가 일단은 그거를 그 어셈블리 코드로 해서 일단은 가세가 되긴 됐거든요. 근데 C로 바꾸면 그게 오버트가 되더라고요.
아, 그 미니 OS 얘기한 거?
아니면 그 타이머.
에서 그렇게 될 리도 없는데. 그 스펙?
네.
그렇게 될 일은 별로 없을 것 같은데. 어볼트 책에 있긴 한데 책 뒤에 한번 읽어봐. 암책. 내가 이쪽에 있어요. 어떤 경우에 어볼트가 발생하는지. 근데 주환이가 얘기한 건 그런 케이스가 아닌 것 같은데 내가 볼 때.
근데 그 서비스 PC를 실행하자마자 그 이게 이제 V바로 가거든요, 걔가. 근데 그 위치를 보니까 어볼트 위치더라고요.
어볼트 위치가 아니라 벡터 테이블에 어볼트 벡터로 간단 말이죠.
네네, 그 벡터로 가요.
그건 글쎄, 뭐
거기로 갔으면 어볼트가 났다는 거.
그렇지, 어볼트가 났다는 거. 일단 어볼트가 나는 케이스가 책에 설명이 되어 있는데 주환이가 얘기한 거는 그 케이스는 아닌 것 같아요. 프리패치 어볼트, 뭐 데이터 어볼트 뭐 그런 게 있어요.
찾아보니까 뭐 두 개가 있다고 하는데 잘 뭔지 모르겠긴 한데.
설명 읽어봤어? 데이터 어볼트의 경우 설명이 있긴 한데.
일단 책은 안 봤어요.
책 한번 읽고 다 설명해가지고 그러니까. 근데 느낌에는 그 케이스가 아닌 것 같아요. 프리패치 어볼트는 혹시 모르겠네. 프리패치 어볼트는 일단 갖고 왔는데 그걸 일단 이제 프리패치니까 갖고 오는 거잖아요, 미리. 실행할 이제 인스트럭션 실제 실행하려고 할 때 실행하면 안 되는 인스트럭션. 그러면 이제 어볼트가 뜨는 거고.
어셈블리로 하면 되는데 C로인데 안 된다는 게 아니냐. 그런 경우가 있을 수가 있나요?
그건 혹시 뭐라고 얘기하기가 어렵네요.
만약 같은 인터페이스 치면은 같은 뭐 데이터나 레지스턴스를 가지는 레스토랑과 치면 그걸 어떻게 이전처럼 연결되는지 레지스턴스가 마우스 인터페이스를 계속 같은 위치에서 계속 보낸다 치면은 그걸 시키면 어떻게 그걸 이전과 다른 인터페이스인지.
네? 마우스 같은 경우는 사람이 차는 거기 때문에 너무나 느리잖아요.
이게 그러긴 한데요. 미시 마우스를 잘 쓰고 있고 그래서 이런 시그널이 발생하는데 레지스터 그거 4개를 어떻게
질문은 인터럽트가 아까 이런 경우인가?
네,
인터럽트가 굉장히 자주 발생하면 어떠냐는
자주는 아니든 IA를 업데이트하고 일부 이것을 있고 그다음에 처리한 다음에 이걸 쓰는 건데 그러면 여기서 이제 다른 다 치면은 기계가 값이 같으면 그 인터넷 처리 끝냈다 그런 식으로.
그치. 읽은 하드웨어 이제 설계를 어떻게 했냐의 문제잖아요. 그 읽은 값을 여기다 똑같은 걸 쓰면 이제 그거는 끝났다고. 여기 보면은 이제 스테이트 머신, 우리가 디지털 롤리웨로 시간에 배웠던 이거 맞지 모르겠는데 파이널 스테이트 머신이 있어요. 이런 걸 설계할 때는 FSM으로 다 설계했어요. 처음에 인터프트 스탠딩 상태에서 스탠딩, 아직 얘가 테이크는 안 됐어요. 스탠딩 상태에서 얘를 읽으면 이제 테이크는 됐다. 엑스큐브 상태. 그걸 하드웨어가 이제 그 상태를 구현해놓은 거지. 그 다음에 이제 여기서 쓰면 그 다음에 이제 아이들 형태로 액티브에서 끝났구나. 아이들 그 인터프트에 대한 아이들.
반복을 하면서
그리고 이 하드웨어를 한번 만들어 보려고 하면 노력을 하면 이해가 더 확실하게 돼요. 하드웨어가 우리가 만든 하드웨어가 아닌데 우리는 사용하는 거기 때문에 답답한 게 있어요. 이건 어떻게 될까? 저건 어떻게 될까? 답답한 게 있지 않은데 우리가 완전 아니에요. 좀 더 고민해 보면 어떻게 하드웨어 설계했길래 이렇게 될까 고민해 보면 많이 틀리겠죠. 그러니까 프로그램 하는 사람 입장에서는 하드웨어 모르면은 답답한 거야. 저 데이터 쉿이 이 하드웨어에 대한 설명을 해주는데 아주 명쾌하게 뭐 이렇게 클럽 바이 클럽으로 설명해 주는 건 아니에요. 그냥 프로그램하는 프로그래머의 입장에서 이렇게 하라만 설명해줘. 기계적으로. 그러니까 이제 답답한 게 있는 거야. 이런 경우는 팀으로 어떨까?
저는 과제 관련 질문인데 그 교수님이 주신 타이머 인터럽트 코드랑 혹시 사용해도 되나요?
그럼
그거 사용하고 혹시 그 UART
UART.
네, 그거 초기화하는 매크로도 써도 되나요?
당연하지. 당연하지.
SGI에서 타겟을 여러 개로 주잖아요. 그때 여러 개가 지정된 상태로 내가 SGI 모든 코어들이 다 처리를 맞춰야 되잖아요. 하나만 처리.
의도가 있겠지. 그거는 이제 예를 들어서 뭐 모르겠어. 그거는 이건 또 소프트웨어 아키텍처의 문제잖아. 소프트웨어. 우리가 OS를 우리가 만들 때 OS를 어떤 기능을 갖고 어떻게 아키텍트 할 건지에 대한 문제가 있었어요. 1 이렇게 썼다면은 의도가 있겠지. CPU 제로하고 6번, 7번한테 인터럽트를 보내겠다. 그거에 의도가 있을 거 아니야. 그럼 걔가 이제 3개의 CPU가 그거를 처리해야 끝나는 걸로 그게 이제 목적이니까 이렇게 보낸 이유는 그게 아니면 왜 이렇게 하겠어?
저런 식으로 두 번째 변화라고 지정하는 CPU 인터페이스가 내가 받아서 처리하는 게 추가 생성돼 있었어.
이렇게 했으면 CPU 룰로도 가고 6번으로도 가고 7번으로도 가니까 거기에 해당 뭐 엑스나로지 있고 해야 되겠지.
그렇게 돼서 상태가 되는
포트가 여기다가 포트가 여기다 쓰는 거죠. 다른 애
여기다가 이제 대상 6칠 대상으로 써놨을 때 7번 써놨을 때 7번이 저거를 어쨌든 둘다 바뀌게 돼.
그렇지.
이런 식으로 바뀌게 돼. 그렇지. 그러면은 사실 그러면 이제 CPU 인터페이스 하나 저거를 어떤 순서에 따라서 바뀌게 될 거고.
그러니까 이제
처리가 됐다.
그렇지. 근데 거기서 이제 이게 있겠죠. 아이디가 일단 있을 거고 아까 얘기한 3이라고 했을 거고
이거는 티가 안 맞으면
그렇지.
버려버리고.
그렇지. 프라이어리티를 뭐 5번으로 했다. 그러면 프라이어리티 레지스터에 세팅을 해놨을 거 아니야. 그거를 그냥 마구잡이로 하는 게 아니라
잘 작동하고.
그러니까 이제 여기다 3도 쓰고 여기다 3도 쓰고 그냥 막 하는 게 아니라 이 아키텍처를 하는 거잖아.
이제 디스트리뷰터가 열심히 얘네들이 최대한 수행하도록 하는 게 아니라 저 파라미터들 수정을 해서 그냥 보내주는 것까지는 딱딱
보내주는 것만 끝나는 거지. 그게 이제 IPI잖아. 인터 프로세서. CPU 간에 인터럽트 보내는 CPU가 진짜 중요한. 근데 의도가 있어야 되잖아. 무슨 목적을 보내는지. 그거는 이제 소프트웨어 아키텍트 하는 사람이 생각을 하는 거지. 그냥 막 보내고서 나 몰라 뭘 하려고 보내는 건지 모르고 보내면 안 되는 거잖아. 뭐 3번 같은 경우는 아까 얘기했던 뭐 태스크 디스패치. OS가 저한테 무슨 태스크를 실행시키게 하기 위해서 보내는 거. 예를 들어 4번은 뭐 스타트업 IPI, 이니셜라이제이션 하고 다른 스킬을 깨우는 용도. 예를 들면 그런 걸 정해놔야 돼. 그러고서 이제 소프트웨어를 만들어야 되는 거지.
질문 잘 연상선. 내가 지금 아까 데모에 보면 SGI만 이렇게 만들면 저도 인터럽트라고 치고 만약에 값을 쓸 때 약간 운이 안 좋게도 원래 쓰여져 있던 값이랑 똑같은 값을 쓰게 되면 그래도 인터럽트 칩을 하게 되는.
여기서 한참 푸는데 이게 바로가 아니라 여기서 썼는데
네네.
원래 있던 값 그대로 썼다.
네네.
당연히 그렇게 됐지. 당연히.
근데 SGI만 다른 거는 따로 붙이는 게 없는 것 같아서 어떻게 가능한지.
여기 써 있는 값과 똑같은 값을 한참 후에 썼다.
네네.
그럴 때 인터럽트 발생하면 안 발생하면 이상한 거지.
그러기는 어떻게 그게 가능할지. 뭐, 똑같은 값이라서 얘가 어떻게 이게
구별할 수 있지. 이게 하드웨어잖아.
네.
뭘로 구별할 수 있겠어? 하드웨어니까 우리가 소프트웨어 보면 값은 똑같은데 어떻게 구별해? 똑같은데 비교하면 뭐 어떤 일이 일어나나 그렇게 생각할 게 아니지. 하드웨어이기 때문에 라이트를 하는 거예요. 최소한 라이트 시간이 있거든. 우리가 베릴로그로 하면 그 라이트 시그널이 있으면 SGIR다가 업데이트 한다. 뭐를 그런 게 최소한 있어요.
라이트 이네이블
여기에 이제 레지스터 쓰기 위해서는 우리가 이런 게 있잖아. IO 장치에 보면 타이머라고 해도
네.
여기에 레지스터가 이렇게 있는데 카운터 레지스터도 있고 로드 레지스터, 스테이터스도 있고 여기다 데이터 쓸 때 어떻게 써? 인터페이스가 있어. 어드레스가 들어가 있고 그다음에 어떤 놈인지 그걸 해. 데이터가 있어요. 서게 돼. 그다음에 이것만으로 되면 안 되지. 리드라이트 컨트롤 시그널이 있습니다. 리드할지 라이트하는 문장인지 구별할 수 있는 컨트롤 시그널이 필요하고 하드웨어적으로는 이거 외에도 자잘한 게 되게 많이 있어요. 구별할 수 있는 방법은 충분히 많아. 라이트를 한다는 자체만으로 구별해요. 라이트를 한다는 자체만으로. 시그널이
네.
하드웨어는 알지. 업데이트 하는구나. 값을 왜 구별해? 업데이트 하는 거 보면은 발생시킨다.
알겠습니다.
PPR 이게 그러니까 이 G라고 표시된 부분이 일종의 마스크가 되는 건가요?
G라고 표시한 그룹. 이게 그룹이고,
네.
그 다음에 S가 서브 프라이어리티. 그룹 프라이어리티, 서브 프라이어리티. 예를 들어 2라고 썼다면은 5비트, 상위 5비트가 그룹이고, 아래 3비트가 서브 프라이어리티인데, 우리 아까 프리엠션을 얘기할 때, 프리엠션은 그룹 프라이어리티가 더 높아야지만, 그룹 프라이어리티가 현재 여기 얘한테 보낸 인터럽트, 이 그룹보다 높아야지만,
그러니까 그룹을 말씀하시죠. 파일 값 자체를
그렇지 아니지. 그러니까 프라이어리티가 8비트인데 8비트가 프라이어리티인데 이거를 두 개로 나눈다는 거지. BP로.
네.
예를 들어서 5비트, 3비트. 이게 이제 그룹 프라이어리티. 예를 들면 서브 프라이어리티.
그러니까 이 애초에 원래 쉐그리더 인터럽트의 프라이어리티 이렇게 됩니다. 그렇지. 그러면 이 값이 타이머라는 건 작다는 거죠.
작다는 거지. 그러니까 그렇지. 숫자. 이 그룹 프라이어리티가 새로 들어온 놈의 지금 얘가 처리하는 인터럽트의 그룹 프라이어리티보다 높다면
네.
그러면 프리엠션을 할 수도 있다.
아, 네.
한다는 것이고. 그리고 이거 받아들이면 보겠다.
아, 근데 갔다면 이제 서프라이어티.
서브는 안 본다. 서브는 무시.
그러니까
프리엠션을
만약에 스윙 중인 애랑 스윙 중이지 않은 애랑 분위기 갔다면 그냥
그거는 프리엠션이 안 되는 거죠.
안 되는.
여기 있잖아요. 여기.
네.
두 가지 조건인데 일단은 첫 번째가 프라이어리티가 들어오는 프라이어리티가
네.
전체적인 그룹하고
네.
상관없어요. 이게 스레시홀드보다 높고
네.
그게 첫 번째 조건.
네.
일단 스레시홀드보다 높아야 되고
네.
그 다음 두 번째 조건은 새로 들어오는 놈의 그룹 프라이어리티가 지금 얘가 처리하고 있는 인터럽트의 그룹 프라이어리티 보다 높으면 그럼 이제 인터럽트를 얘한테 알려주겠다. 새로 들어오는 놈, 이 급한 거다.
그러니까 서브는 안 보는.
서브는 안 보겠다는 거야. 프리엠션을 할 때. 같은 그룹에 있으면 어떻게 돼? 같은 그룹에 있으면 안 된다고 돼 있지 않아? 스펙을 보면
여기
여기 세임 그룹에 있으면은 같은 프라이어리티로 안주한다는 거고 프리엠션을 하는 조건은 그룹이 높아요. 그룹 프라이어리티 높아요. 프리엠션 조건이니까 프리엠션이라는 거는 인터럽트 처리 중인데 얘한테 또 알려줄까? 스피어한테 또 알려줘야 되나? 일단은 뭐 알려줘야 내가 현재 처리 중인 여기서 현재 인터럽트 서비스를 좀 처리 중인데 뭔가 알려줘야 이거 뭐 현재 처리하는 거를 중단하고 얘를 할지 말지를 결정할 수 있잖아. 아무것도 들어오지 않으면 뭐 아무런 뭐 여지가 없지. 아무 들어오지 않으면 CPU를 계속 얘를 하고 있는 거지. 계속 하는 거지. 일단은 물리적으로 얘가 들어와요. 물리적으로 이걸 들어오게 하는 조건, 프리엠션 조건. 프리엠션 조건이 알려줄까 말까? 얘는 뭐야? 기구 구석.